Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits, and in this particular lecture we will be talking about flip-flops. But before we move and talk about flip-flops, right, let's quickly recall that in the previous lecture we spoke about latches, and I want to tell you something that latches are transparent. See, we saw one of the properties of latches where whenever we saw anything at the input, right, the change was directly seen on the output. Whenever for a RS latch, whenever we change reset to 1 set to 0, output q always change to 0. When we changed reset to 0 set to 1, output change to 1, correct. And when we said this is evil, which we said that this should be avoided, any change in the input was directly reflecting at the output immediately, and that's why we say that latches are transparent. Due to this, right, sometimes what we do is we see synchronization problems in the circuit. So basically, let's assume we have two blocks of design. One is having set of inputs which are changing at one point of time, and another other set of design is having an inputs which are changing at another point of time. So the output, which might be used by a third logic, are changing at different points of time. It can lead to various synchronization problems in the circuit. So what we do is, to avoid the synchronization problem, what we do is we use flip-flops, and what we do is we make sure that we respond the circuit output is present only at specific times instead of all the times. So because of this synchronous problem, we what we do is we have a solution for which we use flip-flops. Now let's see what a flip-flop looks like. Right now, in the previous example, I will just draw a flip-flop diagram to begin with, and then we will talk through it, that how this operates. So let's assume we have two latches, right? Let's assume we have a D latch and we have a SR latch over here. And as we see, all the inputs and outputs is like Q bar. SR will have like input S, it will have an input R. Then we have a control bit over here C. We saw a D latch also where we said input, one of the input is D, one of the output is Q bar, and then we have a control signal here. Right now, Q bar is nothing but not of Q, so we represent it using this. Similarly, Q bar is nothing but not of Q, we represent it using a not. Now what we do is all this output of Q we connect to S and Q bar we connect to R. So we'll never have that evil combination because Q and Q bar are complement of each other in a D latch. Now what we do is we get an input D, and then we have an input C which we not it, connect over here. And what we do other than this is we take this and we connect it to C. So now basically if we look at this particular circuit, right, this particular circuit is something which will be known as a flip-flop, and let's try to understand the functionality of this flip-flop. So basically this is nothing but D flip-flop, and it looks something like this. Right, we can put a pointed bracket over here. I would explain the meaning of this later. So basically this is D flip-flop, and D flip-flop has, what is there over here, there is one D latch and there is one SR latch. What we call this D latch as a master, and we call this SR latch as slave, right? So now let's look at the layout over here. What we have is we have a D input, we have a control input C. We NOT this input before going into D, and the non-knotted version goes into the normal version goes into SR latch. So basically it's a back-to-back combination. This is called master, this is called slave. And what happens, let's try to look at the functionality of this particular device, which we are calling it as D flip-flop, but let's see how it differs from a normal latch, and how will the functionality of this particular circuit change as compared to a simple latch. Okay, now let's see this thing. What happens whenever C is equal to 0? Let's assume a case where C is equal to 0. When C is equal to 0, what would happen is this particular circuit is getting input of 1. If this is getting 1, this particular circuit is getting control of 0. If control of this circuit is 0, the output q and q bar would be no change, and this circuit is sort of a cutoff. It doesn't depend upon s and r value, right? So in this particular case, when c is 0, master is enabled, slave is disabled, and q and q bar just maintains its private current state. Q and q bar maintains current state. This is clear, right? When we say c is equal to 0, this input becomes 1. D flip flop enabled, master is enabled. C is 0, this is disabled. When this is disabled, what we say is q and q bar maintains current state from the previous lecture of SR latches. And now when we say master is enabled, what would happen when master is enabled? When master is enabled, whatever input is there on D will be transferred to Q, right? So basically what would happen is Q would be equal to D. Q at next would be equal to D. Whatever is input at D, it is just reflected at a point Q over here, right? But please notice that this input D, like this Q next, which is equal to D, this does not get transferred to S over here, right? Even if it does get transferred to S over here, both are connected. What would happen is this will not reflect on this output Q and Q bar because this particular slave is disabled. Correct? Now let's assume a case where we change C from 0 to 1. Now what will happen when we change C from 0 to 1? Once we change C to 1, master becomes disabled. So basically what happens when master is disabled? Basically what we would say is like Q and Q bar would maintain their current state. Right? We changed from 0 to 1. When we had a value of 0, Q became equal to D. Q sampled the value of D. As soon as we changed it to 1, C changed to 1, master got disabled, and Q bar would maintain the current state. And basically when this at this point of time, slave will get enabled because C has become equal to 1. And once slave is enabled, whatever the current state the of Q was, this gets transferred to this particular output over here. Correct? So basically what we can say is this input, whatever input value of D was, whenever C was 0, it was able to reach at this particular point. It was able to reach at the input of SR latch because this was enabled. Since master was enabled, D was transferred from input to output whenever C was 0, right? But this was not seen over here because this particular slave latch was disabled. When as soon as we changed from C from 0 to 1, what happened was whatever the input over here was to the set signal which was equal to D value, it will get transferred to the output. So basically the input D would be seen at the output only when C changes from 0 to 1, right? So basically what we can say is at time t plus 1, if D changes at time t equal to 0, right? Let's assume our C was 0 at time t equal to 0. C was 0. So what would happen is this particular thing at time t equal to 0 would become equal to D, which is 0, which is become equal to D, sorry, at time t equal to 0. But this D will not be reflected over here because this is off, right? And now assume that at time equal to t, we change C is equal to 1. What would happen? This particular input has a value D, but now this particular master will get disabled. So any changes on D, for the time being, whenever C is equal to 1, any changes in D will not be reflected over here because this particular circuit is disabled. And the value of D which was there on the previous time frame just before C became equal to 1, that value would be transferred to this output, right? So this will remain D. This was like current state at that point of time initially. This was like having current state. Now at time t equal to t, this will have a value of D. So basically qt plus 1, at the t plus 1 instance we would have a value of D, and this t plus instance is when C changes from 0 to 1. And if you see over here, in this particular case, right, what happens is even though if we have a case something like this, if we have a case where let's assume this is C, This is behaving like this. And we have a value D. What will be this output? Let's call it like Qt. Let's call it Qt plus 1. Qt would be what? As soon as C is 0, first circuit is enabled, right? If first is enabled, Qt plus 1 will what? It will directly see a value of D. It will see value of D. Right? When C becomes 1, this is disabled. So value of circuit will remain intact. So basically till the time C is 1, it will remain a value 1. As soon as C becomes equal to 0, again value of D will be transferred to output, and value of D at this point of time is 0. So Qt will be 0. And similarly, as long as C remains 0, the change in D is reflected at the Qt output, and basically what would happen at this point of time, D will again change to a value 1. As soon as C becomes 1, this particular master latch is disabled, and C will maintain its value, like Qt plus 1 will maintain its value. So this will be Qt. What will be Qt plus 1? Qt plus 1 would be something like, as long as C is 0, right? The slave is disabled. Slave is disabled means it will retain its previous state. Let's assume the previous state was 0, so it will remain a value 0 till this point of time. As soon as C becomes 1, the value at Qt would be transferred to the output Q. So the value 1 would be transferred, right? But as soon as it becomes 0, this particular latch is disabled. In that case, it will continue to retain its state, so it will stay 1, right? And what would happen is, as soon as it became 1 again, any change in Qt will be reflected, it will remain 1. So basically what we were able to do in this particular case, right? We were able to, if you see at these 4 waves, what is happening over here in this particular case? In this case, whenever C was 0, first latch was active. Whenever C becomes 1, second latch became active. And any change in input is not reflected at output. If you say Qt plus 1 is not equal to this D signal directly. So basically, whenever there is a change in the edge, whenever C changes from 0 to 1, what we can say is this particular D, value of D was 1. It got reflected on the output. And at the next edge of C, whenever it changes from 0 to 1, this got the value of D again got reflected over here. So this is a flip flop where any change, we these are not a transparent circuit. Any change in D is not directly seen output, but only at specific instances of time. The value of D at this point of time was seen over here. Similarly, value, and then the circuit maintained its value, and then any change at the passage of C, right? Value of D at this passage of the C was again transferred. This was 1. So this is called as flip flop, right? And in this particular case, right, output Qt plus 1 is getting a value equal to D only at a passage of the clock, right? Qt plus 1 is getting a value D at a passage of C. So that's why it's called positive edge triggered flip flop. And this sign is a sign of positive edge trigger, right? So, and there is similarly, like there is something called as a negative edge triggered flip flop also. And a negative edge trigger flip flop is usually represented by this circuit where we just put a C, a not over here. This is the input D, this is C, this is Q, this is Q bar, right? So this is a negative edge trigger. Negative edge triggered mean D will be transferred to output only when C changes from 1 to 0. Correct? Now, if at all, we have to draw a characteristic table for this flip flop, for a positive edge flip flop, whichever we saw, right? Positive edge triggered, where we say next state Qt plus 1 is equal to D at a passage of C. Passage of C is also represented as this. This means positive edge. this particular arrow, right? So if we have to draw a characteristic table, right, we will say we have an input C, we have an input D, we have output Q. This is for flip-flop entire, which is nothing but intrinsically it consists of two latches in master slave configuration, two latches internally. What would happen whenever C was 0, right? Whatever value was D had, output had no change. It was not seen. The change in D was not seen at the output. Whenever C became 1, if D was 0, output became 0. When C became 1, if D was 1, output became 1. So this will be a characteristic table of a POS-H flip-flop. Alright. And whenever we say QT plus 1, where we saying next state of a flip-flop is equal to D. This is nothing but this is called characteristic equation. Right. Now similar to what we see as a D flip-flop, right? We have something called as two more flip-flops are available, which are called T flip-flops and JK flip-flops. Correct. Just to briefly mention about these two flip-flops, we already spoke about D flip-flop where we have output Q bar, we have D, we have C. Characteristic equation of D flip-flop is next state is equal to D. Now we have something called as a T flip-flop where we have an input T, right? It again has same equation Q bar T, and then it again has a C. The characteristic equation of this T flip-flop is it does not depend only on input but XOR with output also. If you see D flip-flop only output depends only on input. For T flip-flop output depends on input as well as the previous state of flop as well. Similarly, in case we have two inputs. We need two inputs. We have something called as a JK flip-flop which has two inputs, and so basically a JK flip-flop would be something like we have J, we have K, we have C, Q, Q bar, and characteristic equation for JK flip-flop is QT plus 1 is equal to JQ bar at T plus K bar at QT. This is a characteristic equation for JK flip-flop, right? So basically, if we see in terms of characteristic table, so operation of D flip-flop is something like D QT plus 1, right? This is operation. If we have to do something like this, D is 0, output is 0, D is 1, output is 1. This is like a reset operation. This is like a set operation, right? If we have to do a similar thing for T flip-flop, where we said QT plus 1 is equal to T is OR with QT. This is a T flip-flop. So we will have something like input T, input Q of T plus 1. The characteristic equation is look something like this. If T is equal to 0, right, anything XORed with 0 is the number itself, my output next state would be equal to present state, which is like no change. If T becomes 1, my next state would be not of QT, complement. Similarly for J and K flip-flop, right, where our next state QT plus 1 is equal to JQ bar plus K bar Q. This is at the time T, at the time T. If we draw, right, input JK, next at QT plus 1, right? If what combinations are possible, 0 0 0 1 1 0 1 1. What happens if both J and K are 0? If J and K are 0, this will become 0, this will become equal to 1, QT plus 1 is equal to QT. So basically this is an operation of no change. If J becomes 0, this is 0, K is 1, this again becomes 0. So this is a reset operation. If J is 1, k is 0, it's a complement of like basically if j is 1, right? What happens over here is j q bar and k bar q is 1. Okay, so if j is 1, this is q bar plus q, which is always equal to 1. So this becomes set operation. And what happens when both are 1? When both of them are 1, so basically this will become equal to q bar plus 0, which is equal to q bar. So this is complement, right? So this is what we spoke about just now. We spoke about if we try to recall, right, what we have spoken about, we spoke that, okay, we spoke about flip-flops. We said latches are transparent, which could lead to synchronization problem in the circuit. So that's why we need to have a flip-flops. What we did was we saw one flip-flop. We created a block diagram of D flip-flop where we kept two latches in back-to-back mode, one being master, another being slave. And then we looked at the operation of if we change a value of C from 0 to 1, how when c is equal to 0 master is enabled, and when c is equal to 1 slave gets enabled, and how the value at the output becomes equal to d depending upon, and that value of d will get transferred only to the output at a pos h, like whatever the value was there at the change of c. uh, this is called as a positive edge triggered because d was getting transferred to output whenever c changed from 1 to 0. Similarly, we have a negative edge triggered flip flop also where d get transferred to output only when there's a change from 1 to 0. Then we looked at the characteristic table for D flip-flop, and then we introduced to something like characteristic equation where we said next state is equal to input D. Then we spoke about two other flip-flops, T flip-flops and JK flip-flops. And in this T and JK flip-flops, we said, okay, in T flip-flop, next state is equal to input XORed with the current state. And for JK, it's like JQ bar plus K bar Q. We looked at the characteristic table for each of these T and JK flip-flops, where we obtained functions like operations like no change and complement for T, and functions like no change, reset, set, and complement for JK. Right, and one thing we saw, one more thing was the nomenclature for positive edge trigger. When we say like this, when we represent something like this, means like a positive edge trigger, which is represented by like this symbol, pointed bracket sort of, and this is something like negative edge trigger where we represent it using a not before the pointed brackets. This is clear, right? So now let's look into one particular equation. Let's do one exercise before we move into that particular analysis, right? Now, can we saw three flip-flops, right? D flip-flop, T flip-flop, and JK flip-flop. Can we create a JK flip-flop using a D flip-flop? JK flip-flop creation using D flip-flop. What does this mean is we have a D flip-flop. We have something like D flip-flop. This is Q. This is Q bar. This is T. This is C. And I have something like a D flip-flop, and we have set of C is connected over here, and we have set of JK inputs which we need to connect to. Somehow we need to have a set of combination to convert this into a JK logic. How do we do it, right? So basically for doing that, can we do that? Yes, we can do that, and let's realize what do we know about D flip-flop. Next state is equal to D, and for JK flip-flop, our next state Q of T plus 1 is equal to JQ bar plus K bar Q. This simply means what I have to do is, right, at if we compare both of this, so basically if this means J has to be D has to be equal to JQ bar plus K bar Q, right? If D has to be equal to J Q bar and K bar Q, what we have to do over here is we have to introduce a combinational logic where we say this input J, this particular input J has to AND with this Q bar, and K bar. So basically K, we forward through a NOT gate. This becomes K bar, and then we tap this Q output. We add this combinational logic and put this as an input to D over here. We connect both of these. So this is how we can realize a functionality of JK flip-flop using a D flip-flop. Similarly, if we have to convert a T flip-flop, let's assume we have to obtain this using D flip-flop. Can we do it? So yes, we can do it because Qt plus 1 of D flip-flop is D, but this is equal to T's or Qt for a T flip-flop. So basically what we can do at the input of D flip-flop, right? We have an input T. We can always XOR it with Qt state and input it into a D flip-flop. This is a D flip-flop. This is a clock input. This is Q and this is Q bar. So basically this Q is connected to this Qt. So this is like a T flip. We converted a D flip-flop into a T flip-flop to get a T flip-flop functionality. Right. These are a few examples of flops, interconversion of few of the flops. We looked at characteristic tables, characteristic equation, and simply right now I wanted to discuss two concepts with you. One concept is a setup time and one concept is a hold time. Right. Now we will discuss concept of hold time and setup time. And this concept is pretty important, and basically let's have our full attention while we discuss these two concepts, right? So basically when we spoke about in journal what is a setup time and hold time in journal, let's assume we have a flip flop which is like D Q Q bar, then we have a C input which is usually a clock input, right? So basically hold time is something for which we have to have input present on the D input so that my output is seen properly, right? To explain it, right, what we have to do is we have to go to a gate level implementation of this positive edge trigger D flip flop. Let's assume this is a positive edge triggered D flip flop. Let's go to the gate level implementation of this positive edge trigger D flip flop. Just to draw it, right, this will be a bit complex, so let's see if we can do it. We have a I'm drawing a circuit diagram for a pause edge trigger D flip flop, right? So basically what we do over here is this is Q, this is Q bar, right? This is nothing, this is S, this is R, and then what we have to do is we need to have a combination circuit over here where we say we have a input here, this input feeds over here, this feeds over here, then we have a C value, and then this particular thing clock input. We have a clock input, then what we have is uh, this is a feedback circuit, and then what we simply do is D, right? And what happens is there's a feedback loop over here where we say that this particular block is connected to. Okay, so basically, okay, this is clearer now. Okay, let's assume this is a pause edge trigger D flip-flop. This is how the circuit of this flip-flop will look like. We will have input D, we will have an input clock C, and then we have intermediate inputs S and R. So basically, it's just like a back-to-back latch, right? So this is a D latch in back-to-back combination with SR latch, and then we have output Q and Q bar, right? Now let's assume we have a case one over here. Case one, correct? Let's try to look at it with the ink color changed, and we will try to understand what happens over here. In case one, let's assume that D is equal to 0 and clock is equal to 0. When which will this will mean that this implies that D is equal to 0 implies what? If this is equal to 0, right? Let's put a nomenclature at different stages, right? Let's call it a point A, let's call it a point B. When D is equal to 0, what would that mean? B becomes equal to 1, correct? NAND gate. And clock equal to 0 implies what? If clock is 0, it will means S and R are both 1, correct? Now B is equal to 1, S is equal to 1, B is 1, S is 1. What would that mean? B is 1, S is 1. This would mean this particular A. S feeds back into this A, both being 1. Would mean that A is equal to 0, right? So basically what we'll get A, S, R, B. A is 0, S is 1, R is 1, B is 1. And since SR is like 1, 1, right? What the thing is, this implies no change in the circuit value, correct? Now in case 1, right? Now at this point of time, let's change clock is equal to change clock, no change, now clock, now change clock to 1. Now whenever we change clock to 1, our initial state was 0, 1, 1, 1, right? So basically D is equal to 0 was implying B is equal to 1, right? B is equal to 1, S is equal to 1 was implying A is equal to 0, right? Now whenever we have S is equal to 1, B is equal to 1, and clock is equal to 1, what would this implies? S is 1, B is 1, clock is 1, R will become equal to 0, right? Once R will become equal to 0, this implies S and R is equal to 1, 0. This is a condition of reset, which means my ASRB is nothing now, but it's equal to 0, 1, 0, 1. If you see over here, right, whenever we moved clock from 0 to 1, only R changed, and what it took for R to change, it took one gate delay. Basically, what whenever we made clock is equal to 1, this S was already 1, B was already 1. Just that when this clock became 1, after one clock delay, what happened? Our R has changed to a value 0, right? Basically now if you say R has changed to a value 0 with one gate delay. Now let's assume a case where the input D changes after R has stabilized. If the input D changes after R has stabilized, there will be no effect on the output. Do you guys agree with it? Because R has already become 0, right? Once R becomes 0, if D changes, once R has stabilized to a value, there will not be any change in the output. And this is called as a hold time. right? This but is this concept of hold time clear over here? Okay, now let's move ahead. Now let's move on to a case 2. Inside case 2, what we will do is let's discuss something like this thing. In case 2, let's say d is 1, clock is 0. If clock is 0, clock is equal to 0, this implies r equal to 1 and s is equal to 1, and d is equal to 1 would imply r is equal to 1, d equal to 1 and r equal to 1 would imply b equal to 0, and b is equal to 0 would imply what? If b is equal to 0, it would imply a is equal to 1. I hope this is clear. Let's second case, when d is equal to 1, clock is equal to 0. Since clock is equal to 0, we would know that r and s both will become 1, and if r is 1 and d is 1, b will become equal to 0, and if b is equal to 0, a will be equal to 1. This would mean the value of ASRB, all the intermediate points which we have coded, is 1 1 1 0. S and R are 1 1, so this is a case of no change. Now in case 2, let's make clock is equal to 0. Correct? Now let's make in case 2. What would happen in such a case? In such a case, what would happen is my initial starting point was ASRB was equal to 1110. If A is equal to 1, so I said is clock is equal to 1. If A is equal to 1, clock is equal to 1. What would this mean? If A is 1, clock is 1, this would imply A comes here, clock comes over here, S will become equal to 0, and if S becomes equal to 0, R would become equal to 1. Right? So basically look at it. While I am changing these values, we already reached a predetermined stage. We assumed that, okay, let's assume the state of a system is this. Then we change the clock value, and then we said like, okay, when we change the clock value, only R changed. Right? Similarly, we are taking one more case over here. Let's assume initially D was 1, clock was 0, and then based upon this, we obtain this state of the system. Now what we are doing is, as soon as we change the clock to 1, we are trying to obtain the state of system. If R is equal to 1, D is equal to 1, right? What would that mean? This would implies B equal to 0. R and D both being 1 will make B equal to 0. And B equal to 0 will imply what? If B is equal to 0, this will imply A is equal to 1. If A is equal to 1, what would this mean? This would imply S and R are 0 and 1. Right? Basically, now what has happened over here is S has changed from 1 to 0. Now only A has changed here after 1 gate delay. In this particular case, only S has changed after 1 gate delay. In here, in this case 2, this happened when we moved clock. In case 1, this changed after 1 clock delay. Right? This will again be called as a, so basically if now D changes after S has stabilized, there will be no effect on the output. This is called hold time. Right? Now let's go further. Going from D equal to 0, clock equal to 1, from D equal to 1, clock equal to 0. Now let's look at one more case where my D was 0, clock was 1. This is our final state, and we are going to this state from to this, from D is equal to 1, clock is equal to 0. Basically this state, in the previous example we made clock is equal to 1, right? In this particular case, what we are doing is we are just changing D is equal to 0, and initial state was this one, ASRB 1110. Now if D is equal to 0, this would implies B is equal to 1. If D is 0, this will imply B is equal to 1. Now our clock, right, is 1. From this stage we went into this stage, right? We made clock is equal to 1, and since clock is equal to 1, initial stage was A is equal to 1. This would imply S is equal to 0. S is equal to 0. S is equal to 0 implies A is equal to 1. S is equal to 0 would imply A is equal to 1. S is equal to 0 would also imply R is equal to 1, right? Now what is happening is we have got a result saying that ASRB is what? ASRB is 1011. 1011. This is a wrong result, right? So basically what we can do is we can't go from this sequence to this sequence. We can't say that at one point of time when our D is 1, clock is 0, we can't change if we toggle both of them together, right? If we toggle D to 0 and clock to 1, what would happen is we would see a wrong result at the output, because eventually what we would want is whenever D changed to 0 and clock became 1, we would expect output to have 0, right? But that is not the case. So instead of going from case 2 to this particular case, right, uh, it will take two gate delays setup to for this to happen. So basically what it means is we need to have D input present at the input before clock toggles for some amount of time before we can toggle, or before any one of them could toggle. This is a concept of setup time. I hope this was clear, right? We spoke on it for a good amount of time, where we looked at two of the cases where we went from a case where we said, okay, our input remains the constant and our clock changes. If our clock changes, what would happen is the same change is reflected in the output, right? So basically what we did over here is when we had a situation of D0 clock 0, then we kept the input stable for some amount of time and we changed the clock to 1. And what we saw was that particular thing was reflected on the output, where our reset became is equal to 0 and output will become equal to 0. So what we saw was D was getting reflected on the output when the clock changed, and there was a 1 clock delay for this to happen, right? And that is called as a hold time. Similarly, the case where we took, okay, D was 1, clock was 0, and then we kept D as 1, and we made clock equal to 1. So basically what we were able to see, we were able to see output of 1, right? We were able to see output of only S getting changed at the output, with only one gate delay, and that gate delay was of the S gate. And we again say, okay, this gate delay is something like a hold time for which we can see output. Basically the output would remain stable if we have that gate delay before D changes, right? So the input has to be kept stable for that much amount of time for it to be seen on the output, correct? So that is called the hold time. Now then what we did is we did a case where we said we directly went from D is equal to 1, clock is equal to 0 to D is equal to 0 and clock is equal to 1. Basically we toggled both of them together, and once we toggled both of them together, right, output result we were not seeing correctly, we were seeing a wrong result at the output. And basically, and this is the concept of setup time, that there should be a minimum amount of delay between both the inputs changing so that the output is observed correctly. So this is a concept of setup time. I hope this was useful, and this particular concept of setup time and hold time is clear, right? Just before we end the lecture, I want to talk to you about one more concept, and that is something like synchronous or asynchronous inputs, right? So we already saw a D flip flop, where we saw D flip flop is something like Q, Q bar. This is not, this is Q, this is D, and this is clock. D, clock, Q, Q bar, right? Now, what in case like the system is not initialized properly? What is the, can we control the values of Q and Q bar? We don't know what all these values would be if at all we don't specify some input, right? So one, basically what would happen over here is we could set the initial value synchronously at the next pause edge, but this actually makes the circuit design very difficult. So that's why most of the flip flops would provide direct inputs or asynchronous inputs that would directly help us set or reset the circuit regardless of the clock event, right? So what would most of the circuits would have? They would have a pin. either a reset pin or a set pin, right? And based upon supplying this value, if at all we make r bar is equal to 0, right, we will change q to 0 and this will ensure q bar is 1. So basically it's like having a deterministic initial state of the system. Similarly, if s bar is equal to 0, this would mean q is equal to 1 and q bar is equal to 0. This is again a deterministic state. So before a flip-flop is used, if we have these pins, we can set or reset to a known state. So that is concept of one of the direct inputs. And this is how we represent it. We, instead of having both of them pins together, we can have only one pin, say a reset pin or set pins, and depending upon the value we supply on one of these pins, if we have only let's assume r bar pin, if r bar is equal to 0, output would be this. If r bar is equal to 1, this will correspond to this particular state. I hope this lecture was clearer and we spoke about flip flops. We started with developing a D flip flop using two latches. We looked at multiple constructs over here, how D changes moves from input to output at a pos edge of a C. We spoke about positive edge triggered and negative edge triggered flip flops. We looked at the characteristic equations, and we spoke about two new flip flops, T and JK flip flops, and then we derived the characteristic table as well, and we converted a D flip flop into a JK and T flip flop. Then we explored the concept of setup time and hold time, and we see that okay, how changing a clock will transfer input to output, but how much clock delay, how much gate delay it would take for the input to be transferred to the output. Similarly, when we change both the inputs together, D and clock, we saw that we could get a problematic situation, and that's why we cannot change it together. We need to have some sort of setup time before we change the clock input also, or the D input, before the clock edge arrives. Then we saw one variations of the D flip-flop, or any flip-flop for that matter, where the states Q and Q bar at time t equal to 0 are usually undeterministic. To ensure Q and Q bar are deterministic, what we do is we add a set of set or reset ports to either make sure that values are 0 or 1, or 1 and 0. And this is something we call as direct inputs. So thank you for attending this lecture. Stay tuned for the next one.